Have you ever wondered how we're supposed to build the cities of the future without kind of flying blind? Well, today, we're going to dive into this incredible team up between satellite imagery and artificial intelligence. It's completely changing the game for urban planning, and believe it or not, it's making our cities way smarter and a whole lot more sustainable. So, let's get right to the heart of the problem. Our cities are growing at an absolutely breakneck speed. And this crazy fast urbanization creates what you could call a visibility gap. I mean, our traditional planning tools, they just can't keep up with the changes happening in real time. It leaves planners trying to make huge decisions basically in the dark. And the scale of this, it's just staggering. Right now, you've got 4.4 billion people. That's 56% of everyone on Earth calling a city home. And get this, projections show that number is going to climb to 68% by 2050. I mean, that puts an almost unimaginable amount of pressure on our urban spaces and all our infrastructure. And here's the central conflict that comes with all that pressure. As our cities expand, we see this great replacement. Essential green infrastructure, parks, wetlands, all this stuff that breathes, is being systematically paved over by gray infrastructure, like concrete and asphalt. And this is way more than just an aesthetic issue. It has really severe consequences, like way more flooding and these dangerously hot urban heat islands. So, this all brings us back to that fundamental challenge, right? That visibility gap. The old school way of mapping things is often years behind what's actually happening on the ground. So the crucial question becomes, how can you possibly make smart decisions for a city when you can't even see what it looks like today? Well, the answer, believe it or not, starts in space. The solution lies in our ability to take all this raw satellite data, literally millions and millions of pixels, and transform it into a clear, intelligent, and most importantly, actionable picture of our planet's surface. Okay, so it's basically a three-stage process. First, the satellite up there snaps the raw image. Then, that image has to get cleaned up through something called atmospheric correction. And finally, we analyze the unique light signature of everything down on the ground. Let's break down exactly how each step works. So, atmospheric correction, think of it like cleaning a giant, really dirty window. Satellites have to look down through our entire atmosphere, right? And all that stuff, haze, water vapor, you name it, it distorts the picture. So this digital cleaning process removes all those effects, making sure the data we're looking at is a true, crystal clear representation of the surface. Now this brings us to a really cool concept, the spectral signature. You see, every single material on Earth, a tree, a puddle of water, a concrete sidewalk, it all reflects light in its own unique way. This pattern is like a fingerprint, and it's the absolute key to telling us exactly what we're looking at, all the way from space. And here's how that works in the real world. Healthy plants, for instance, absorb a lot of red light, but they strongly reflect near-infrared light, something our eyes can't see. Water does pretty much the opposite. We can even tell concrete from asphalt, because concrete has a higher albedo, which basically just means it's more reflective. These are those unique fingerprints our AI is going to learn to read. So once we have that clean data and we can read these spectral fingerprints, how do we process it all? I mean, it's a ton of information. That's where our AI planning partner comes into play. We use machine learning algorithms that can analyze these patterns across millions of pixels at literally superhuman speed. And there are two main ways to do this. You've got random forest, which is kind of like a super meticulous analyst looking at each pixel one by one. It's incredibly fast and really accurate on that single pixel level. But then you have a convolutional neural network, or CNN, which is more like an artist. It doesn't just see the individual pixels, it sees the shapes and patterns they form, giving it a much better feel for the spatial context of a city. And the data really shows this difference. You can see random forest has an impressive 93 to 97% accuracy on a pixel level. But because it lacks that spatial awareness, you sometimes get this salt and pepper noise in the image. The CNN, on the other hand, while it has a slightly lower pixel level score, is way better at mapping complex real-world things like road networks because it actually understands the context. I mean, the level of precision these models can get to is just remarkable. They can tell the difference between grass and the leaves on a tree canopy. They can differentiate an asphalt road from a concrete building next to it. They can even spot wetlands by analyzing how an area changes over a series of images. This lets us generate these incredibly rich, detailed maps that really empower city planners. So, this is the crucial part, right?
How do we take all this amazing technology and translate it into a real-world impact? Well, these digital maps are quickly becoming the new blueprint for how we build more resilient and sustainable cities. Planners can now almost instantly see the hottest parts of a city and target their tree planting and cooling initiatives right where they're needed most. They can spot canopy deficits, map flood risks with incredible precision, and use this always current data to inform things like zoning laws. This is a total shift from reactive planning to a proactive, data-driven strategy. And this isn't just some sci-fi future, it is already happening. Take a look at Milwaukee's homegrown program. They are using exactly this kind of data-driven approach to find vacant lots and transform them into valuable green spaces that help manage stormwater, cool down neighborhoods, and just generally improve the community's well-being. It's also completely changing how we deal with flooding. When you have maps that are 87% accurate in predicting which areas are flood-prone, planners can be absolutely surgical in their response. So instead of just building bigger concrete pipes, they can deploy a smart mix of green infrastructure, like rain gardens, right alongside traditional engineering to build true climate resilience. And as powerful as all this is, it's really just the beginning. The next big leap forward is moving from these static snapshots in time to a live, always-on, autonomous view of our cities and, well, our entire planet. The evolution of this technology is just mind-blowing. We've gone from systems like Landsat, which looked at the same spot every couple of weeks, to new constellations like Planet's Pelican, which can deliver super high-resolution images of the same location multiple times in a single day. This isn't just an improvement, it's a complete paradigm shift. So what does that really mean for us on the ground? It means that visibility gap we talked about is finally closing. Planners can track construction projects in near real time. They can assess damage within hours of a disaster. And they can proactively enforce environmental laws because they have an immediate, persistent view of what's happening. And this has profound implications for social equity. As this quote points out, traditional ground monitors are often few and far between in rural or low-income neighborhoods. This objective, wall-to-wall satellite data can shine a bright light on those disparities. It provides the hard evidence needed to advocate for environmental justice and make sure everyone benefits from a healthier environment. So we end with this thought. For pretty much the first time in human history, we can see our urban world not as it was months or years ago, but as it is right now. The question isn't about our ability to see anymore. It's about our collective will to act. How are we going to use this incredible new vision to build a better, more equitable, and truly sustainable future?